Welcome everyone for today's talk on Flink. Today, my colleague Shaoxuan and myself is going to talk about Flink's improvements to TableAPI and SQL. I joined Alibaba since the end of 2014. Before that, I worked at some other companies. First, I'm going to give some background on why we are on Flink and Alibaba. Then I'm going to explain why we look into TableAPI and SQL. Finally, Shaoxuan is going to give some detailed explanation on how Flink TableAPI and SQL works. Here's some background about Alibaba. Alibaba operates the world's largest e-commerce platform, Taobao and Tmall. This platform recorded a gross merchandise volume of almost $400 billion in year 2015. And on November 11th, 2016, it recorded almost $18 billion of sales in a single day. This is huge. And we are part of the Alibaba Search group. Our group is responsible for providing the personalized search results and recommendation results to various search products inside Alibaba. Search is one of the major drivers of user traffic in our sites. The sites we support include Taobao.com, Tmall.com, AliExpress.com, and Alibaba.com, and many others. We started looking into Flink about 2 years ago, and we were very impressed by the architecture of Flink. So we decided to use Flink as our computer engine. We discovered a few issues that can be potential problems in large-scale production. So we started the Flink project. This project is trying to make Flink work well for the very large scale at Alibaba. So currently, Flink is running on thousands of machines in production. It also supports key scenarios such as search, recommendation, advertisement, security, such kind of things. It's all these are mission-critical business for Alibaba. One thing I want to stress is Flink is fully compatible with the Flink API and its ecosystem. Now let me give you some example of how we use Flink in Alibaba. This is a classical example of search. To provide a search service, you first need to generate a set of documents that can be searched. In our case, the set of documents are basically the listings in our e-commerce site. For example, like a list of the products that can be sold. So to generate all this, the list of all such items, this sounds simple, but in practice, it's a bit more complicated because the data for these listings are scattered in different data sources inside the company. For example, the price information, inventory information, such kind of information are usually stored in systems like MySQL. But other kind of information, such as the classification of each product, the classification tree of the products are probably stored in some Hive table. So the first step we do is we synchronize the data from these different data sources into our edge-based tables, into our own cluster. Once all the data is in our edge-based tables, we do the second step, which we call join step. In this join step, we merge the data together and apply whatever necessary business logic to process the data and produce the document that can be searched. The produced documents get stored in the result table in HBase as well. Once the result table is available, we can export the documents from result table to external systems such as search engine, and we can start serving these contents to our users. One thing I want to point out is each one of these stages actually contains two pipelines. The first pipeline is what we refer to as the full build pipeline, which usually runs every day, runs daily, and processes all the documents to generate a snapshot. But the contents of the documents can change after the snapshot is generated. For example, when user purchase an item, the inventory will change. Such inventory change, such kind of change had better to be reflected in search engine as early as possible, because if some item is already sold out, it doesn't make much sense to show it in the search result, because when user click on it, he cannot buy it. It's not the best experience. To do this, we also have an incremental pipeline that delivers updates to the search engine at real time. We converted both pipelines to use Flink last year, and we were very happy with the result. Once we did this conversion, we noticed the reliability and the scalability of the system gets much better. So this is all good, but we are engineers. We always look for we always look for whatever improvements we can do, what we can do better. So we figured out there are two things we can make it better in the current system. The first one is we have two pipelines, which basically, the first is the batch pipeline, the second is the streaming pipeline. Today, Flink provides the dataset API to do batch processing and the data stream API to do streaming processing. Because these two sets of APIs are different, which means we will actually need to have two separate code base for the batch pipeline and the streaming pipeline. This not only makes it difficult to maintain our code base, it also makes the logical consistency between these pipelines non-trivial, because there is some strong consistency requirement between these two pipelines. The results produced by these two pipelines should be compatible with each other. Ideally, we really want a single code base that can run in either batch mode in our daily jobs or in increment mode as real-time update jobs. Even better, we want to mix them together. Like we want to run a batch job to generate a snapshot and run the streaming job to update to provide the incremental update to this snapshot. So that's one thing we hope to improve. We are looking for a unified API that can support both batch and streaming. The second thing is the data stream API and the dataset API are relatively lower level. So user need to tell us exactly what to do in each step of the computation. As a result, user need to be careful in how he writes his code to achieve the best performance. Ideally, we only want user to tell us the semantics of their computation and leave the performance details to the system. The system can make whatever optimization to deliver the semantics of what user described. This problem is solved in the database community a long time ago, and the solution is called SQL, as everyone already know it. SQL is a proven way to describe data processing at very high level. It's one good thing. It's not only simple to learn. There is another good thing about it is it's sufficiently high level. It's sufficiently descriptive, which allows the system to do complex optimizations. This freedom is very important to us. In addition to SQL, we also looked into TableAPI. TableAPI is basically a Scala version of SQL. In some cases, it can be a bit more convenient than SQL. For example, if your data processing logic contains multiple SQL statements, it can be tedious if you write it in plain SQL. But with TableAPI, it's very straightforward. And another advantage of TableAPI is in case we do need to have some extension to SQL, it's much easier to do in TableAPI, but a bit more tedious to do in SQL. So we plan to use both SQL and TableAPI to simplify our user code. This is good, but as everyone knows it, SQL only works for batch. But in our first goal, we try to unify batch and streaming. So we need to solve the problem. How did we get SQL working on streaming? So let's look at how SQL works for batch. In batch, the first thing you have is, before you write a SQL, you usually have a set of input tables and a desired output table. Then you use SQL to express your data processing logic that converts, that transforms this input table to your output table. So table is essential for SQL. Without table, there is no starting point for SQL. But apparently, a traditional table in big data is not enough for us. The problem is the traditional table is static. We will need to, as it turns out, to unify streaming and batch. It's important to generalize the concept of a static table into dynamic tables. A dynamic table is basically a table whose content can change over time. With this concept, it's possible to establish some equivalence between a string and a dynamic table. This is what we refer to as the string and table duality. So in this picture, on the left side, we show you a string, and on the right side, we show you a dynamic table which has a compatible schema with the string. The way to look at this is you can imagine the string on the left side as a changelog of the dynamic table. So as you get more entries from the string, you apply these entries as changes, as updates to the dynamic table. For example, when you get the first hello Wang, you basically insert a hello Wang in the dynamic table. But when you get the second hello 2, you update the content of this dynamic table. So during this operation, we will refer to this operation as the apply operation. With the apply operation, we can convert a string into a dynamic table, which has the compatible schema. On the other hand, if we have a dynamic table, we can derive its change as a changelog. So because this dynamic table changes over time, so for each update, we will include the content of its update in the string. So you will get a string over time. This process is what we refer to as the changelog. With these two operations, we can establish the equivalence. With these two operations, these operations are kind of inverse to each other in the sense, if you have a string, you do the apply operation, you get a dynamic table. And on this dynamic table, if you derive its changelog, you get back the original string. You can also do the other way around. If you have a dynamic table, you can derive its changelog. And if you use the changelog to apply it to another dynamic table, basically you get the same dynamic table back. So these two operations compose to identity in either way. As we know in mathematics, these are inverse to each other, which basically means the string and the dynamic table contains the same information. They are in some sense equivalent. So this is the way to establish the equivalence between a string and dynamic table. Now we have our basic concept, dynamic table. Dynamic table is a generalization of a static table. In batch mode, the basic building block for batch processing is a static table. It can be considered as a special case of a dynamic table. In the case of streaming processing, you need dynamic table that rarely changes over time. Now we have the basic building block to unify string and batch processing. Let's look at a bit more detail on the how dynamic table works. So in the previous picture, when we apply the changelog, there are actually two possibilities. The first possibility is the dynamic table does not have a primary key. In such case, each record in the string will become a new record in the dynamic table. In the second case, the dynamic table actually has a primary key. So in this case, the changelog, when you apply the changelog, it may update a previous record in the dynamic table. So these two we refer to append mode and update mode. On the other hand, when we derive changelog from the dynamic table, we also have a little bit of freedom. When we derive this changelog, we may only include the new value of the updates. In this case, we will call it as read mode because this changelog is good for reproducing the dynamic table. but there is another mode which is redo plus undo mode. In this mode, when an update happens, we not only include the new value in the changelog, we also include the old value in the changelog. So if you play the log backwards, you can actually undo all the updates in your dynamic table. Okay, now let's look at with dynamic table. Let's look at how we do SQL in the case of streaming. Suppose in the case of string processing, what you usually have is you have a set of strings as your input string, and you have a desired output string. You need to describe your logic that converts the input string to your output string. What you do first is, first you conceptually convert this string into dynamic tables with the table string and table duality. After the conversion, you basically get a set of input dynamic table and an output dynamic table. Then at each time t, you can write the SQL just as batch query that describes your computation logic, the data processing logic. So dynamic table, this batch SQL will actually be describing the computation of your streaming process. So to summarize, a dynamic table generalizes the concept of a static table. So it allows us to unify batch and streaming. And SQL serves as the unified way to describe data processing in both batch and streaming mode. So what is string SQL? Basically, the way we do string SQL is there is no such thing as string SQL. There is only batch SQL. Batch SQL works in both batch mode and streaming mode. We do not need to invent a new type of thing. Okay, next I will ask my colleague Shaoxuan to give a bit more details about Flink SQL and TableAPI.
Thank you, Xiaowei.
Thanks.
Okay, good afternoon, everyone. I'm Shaoxuan. I would like to continue our talk on Flink TableAPI and the SQL. This is my agenda. So I will first introduce the streaming inner join, which we have heavily used in our production. And then followed by this, I introduce three functions, UDF, UDTF, UDAGG. Because we think those functions is very helpful for user to describe their business logic. And together with UDAGG, I will introduce a retract, which is very important building block for UDAGG interface and also for streaming. At the end of the talk, I will introduce recent work on the Over Aggregates. Before we go to the advanced TableAPI and SQL, let's just take a look at the simple example of SQL select and where. Assuming you have table, you have multiple columns, and you can select whichever the column you're interested. In addition, you can add in a where clause where you filter the data. For instance, in this case, you have table and your filter, it turns out giving only 2 rows for you. So if you are lucky, all the information columns you're interested in one table, then you are done. But what about if the data is in different tables? Let's say in this case, the name, stock, price, sales are separated in 2 tables. One on left table, one on right table. If you still want those data, basically you need to do the table join. In the streaming, it's a streaming join. And if you still want doing the same way to get your data, so you apply stream join, but remember the streaming could be out of order. So some case might existing in the left table, say this number 3 on the left side is not on the right side. So when you're receiving 3, you don't want to, join empty and send out to the downstreams. So in this case, you want a complete result, then you need to do the inner join. So together, streaming inner join will do the same job as previously, even though the data is separate in 2 streams. So how do we model this? So the simple way would just buffer the data in the memory. Then you quickly go out of memory. You get the memory problem. Another problem would be reliabilities, failover, exactly one semantics. So one simple approach we came up is that, let's use state. Fortunately, the Flink is very good at managing state. Before Flink, other system is difficult to handle state. Flink is designed its first class, first state. We can easily use Flink state management to this. Basically, the idea here is that we're using two state, left state for the left table, right state for right table. When you're receiving anything, you just buffer your data in the state and checking if the peer side has the data or not. If it has, then you emit to the downstream. If it doesn't have, then just keep it there. This TableAPI SQL is proposed and discussed in Flink 5.8.7.8. If you're interested, you can take a look. Next, I will introducing UDF, UDTF, UDAGG. So with select, where, join, basically you allow the user to describe your data processing logic. But there's still a lot of huge amount of needs. User provide their business logic. How you're going to do this? Using those three functions. So UDF, UDTF, UDAGG together help user to describe their business logic. What are the difference among those three? The difference is very simple. The difference there, they have difference on type of their input and output. UDF take Scala as the input and one Scala as output. UDTF take one Scala but generate a table. UDAGG actually is opposite operation to the UDTF. Comparing to the UDTF, it's taking a table, generate one Scala. That's a major difference we observed. And together with UDAGG, I'll introduce the retraction. As I mentioned, it's very important part for UDAGG interface. Cool, let's start. Let's take a look at the UDF. UDF is Scala to Scala. It's very simple and straightforward. If user want to describe some logic, they just define a contract method, which we call the eval function. If you look at this example, in eval function, you can overloading with different parameters, different types. And recently, we have enhanced UDF to let it support variable types and arguments. And once you create this class function, you can register it and use it in the SQL query. UDF is simple and very useful, but it has a limit because it's only generate one line, one column. What if the user want multiple lines, multiple columns? For instance, in this case, user giving you a line, a string has a space and the shells. It wants using the string to split the lines and the shells split the columns. So in this case, you basically have a Scala and transform to a table. The table has two columns, name and age. Then we need a UDTF. UDTF works very simple and similar as the UDF. It still allows user to implement a eval function. And in the eval function, it implements its own logic. How does the user split the lines, split the columns? And you create a class similarly and write a SQL query. We have shipped UDTF in Flink 1.2 last year. Okay, now let's go to the UDAGG. So UDAGG, as I mentioned, is a table to Scala. It's very powerful and very, very useful. Flink itself has built-in aggregates, like sum, average, minimum, maximum. And it's not sufficient enough because imagine user, what about if user wants some aggregates? It's not defined in the built-in aggregates. Say with the average count, with the average aggregate. So that means we need basically need an interface to let the user, allow user to register user-defined aggregate function. Okay, let's start. So before we define the UDAGG interface, we needed to understand how the aggregation works. So UDAGG is transforming table to Scala. So we basically apply each row of the table to the AGG, and one by one. So the intermediate state inside the AGG, we call it accumulator. So basically, you need one function to create an accumulator, init accumulator. Then you apply the rows. The table has multiple rows. You apply those rows to the accumulator. That's a method we call the accumulate method. Once you have accumulator method, and when the aggregation completes, you need a get value method to get the aggregation result. It's simple, and that makes the most simple the UDAGG interface. So for instance, we having this interface on the left top side. It has a create accumulator, get value, and accumulate. The above two is in the interface because their input and output is defined and determined, while the accumulate is provided by the user. It can take in dynamic input. So it's a contract function like the eval function for UDF and the UDTF. With this interface, you can create a very simple aggregate. It's called a weighted average accumulate. And implement the three functions, then you write a circle, then you will get the aggregation working, user-defined aggregation working. So good, now we have the user-defined aggregate. Are we good now? Let's see some examples. Let's say a more complex problem. If we want to count the total visits on our Taobao web page in real time, how we are going to do this? So imagine you have millions visits, even 10 million visits per second. And if you're receiving all those visit events and send to one single node, boom. So the node cannot handle this. It doesn't have sufficient capability to process all the visit traffic. So another better approach we came up is two-stage aggregate. We call it the local global aggregate. So in first stage, we partition the traffic to different nodes. Basically, we split the traffic, split the loads. And as the first stage, we do the partial aggregate. Then we get the accumulator. At the second stage, we merge those accumulator and having one single accumulate. And then you can get value from that accumulate. So the interface of a merge is that you have a collection of the accumulator. The output is just accumulate. So as I mentioned, motivated by this requirement and also some other scenarios very useful for using the merge, let's say session window merge. So we decided to put the merge method into the aggregate interface. Good. Now we have accumulate and merge method. Let's see another more complex example. So in this case, you're receiving the wording as a stream, a lot of different words. It can be repeated. And if you want to if you want to check how many words counted in 3, 4, 5, basically you want to know those words counting on 3 and how many words has been counting for 3. It's frequency of the 3 or frequency of the 4. How we do this? We do 2 steps. In the first step, we group by the word and we calculate the count. The second step, we group by the count. Then we calculate the frequency on the count. So initially, the table looks like this. So you already have 3 record, hello, word, and bark. You get the final result. Count 1, it has appeared 3 times because those 3 words are differently. And then let's see, when a new record coming, hello 1, what happened? Hello 1 count from 1, jump to 2. Okay, so the intermediate table will generate another traffic 2-1 to the final result. Yes, we do insert a 2-1 in the final result. Is it correct? No, actually we got something wrong here because the value for count 1 is not correct. After the hello jump to 2, there are only 2 words, word and bark is counting to 1. So the frequency of 1 should be 2. Why is this happening? So when we're increasing 1 to 2, we did add 2 to the result, but we forgot that the hello has been changed. The count 1 has changed. We need to tell the final result, hey, 1, there's some word is appear to 1, but now it's changing. So you need to retract this count. So this is the approach for this motivate, and this is the approach for retract. Basically, we need a way to realize this. And when we realize this, we adding the highlight by yellow, we call the retraction. We adding a retract message. When you accumulate 2 and you retract 1, then you will get the correct result because now the frequency for 1 is 2. So this tells us basically we need a retract method in the UDAGG. So we have accumulate merge, then we need another method called retract. Okay, how this amazing thing happening? So we need a way basically to understand and tell when the retract is needed. We have explained how the retract mechanism works, but does retract always necessary? No, of course not. It's very expensive because you send a retract, and sometimes the downstream doesn't need a retract. So we need a way to check the execution plan, detect where the retract is needed. Luckily, Flink using callset. Callset has a query optimizer. We do this in the step of the query optimizer. So when you write a query, we send to the query optimizer understand your plan and detect where the retract needed or not. Okay, so the retracts are very big and complex. I'm hoping this gives some just initial background about this. And if you're interested, you can look at this Flink, and we are going to also post a flip for this. Okay, so this completes the UDAGG interface. This has 2 interface inside abstract class, create accumulator, get value. Then it has accumulate, merge, and a retract method. And this part almost done. We plan to ship it in release 1.3 for Flink. By the way, I forgot one thing to mention, that the highlight by red, that's a must-have function. That's a function ensure the aggregation works. And the merge and the retract is optional function. So you don't have to provide them always. But if it's good if you provide it, because for instance, if you provided the merge method, the query optimizer knowing that, okay, this guy's good, provide the merge. And it's checking the conditions to see if there is possible or get any benefit if I do 2-stage local global aggregate. Similarly, it will check in retract method if it's existing. If it's existing, it will do the thing correctly. Okay, let's complete the functions and the retract. Then let's come to the over aggregations. So up until now, we keep using the grouping, so aggregate with group by as an example. So aggregates can be used with group by, and there is another very useful use case you can apply aggregates is over aggregates. So the major difference between over aggregates and grouping aggregates is that the grouping aggregates basically group the data, and for each group, it just generates one result. For the over, it generates each result per each record, always. So the over is very helpful in some cases. For instance, moving average and ranking per each row. In this case, let's say you have input with different time, item ID, and the price, and you want to calculate the moving average for the last five seconds. So basically, you have certain range window, and the over can achieve this because the user want to having exactly output for each line. For instance, for this case, you have 2 record has 5,000 milliseconds. If you're using grouping window, you cannot get 2, you only can get 1. But the over can ensure you always getting 1 result per each row. Okay, so the group over aggregate together, so there's a grouping method. You can either using grouping by or over clause, and also window another good way to providing you the a certain amount of data grouping method. So right now, in Flink, we're supporting tumble session sliding window time count, and we also support the over range rows windows. And for the time tabs, we have event time and the processing time. And one thing I want to mention is that here, if the processing time is dedicated for streaming, it's not well defined. If you want having exact same results similar as a batch, you have to using the event time. So yeah, we have working very closely with the Flink community, with Fabian and Timo, and we almost achieved all the group over aggregates. We are currently working on the table API for the over aggregates. I think that's all for technical part. And as a summary, so Xiaowei has mentioned this continuous query on dynamic tables. So we, Fabian, me, and Xiaowei has posted one blog on Flink. You can check it out. And UDF, we have some improvements, and will be already in Flink Master. Will be releasing 1.3. UDAGG, we also target for release 1.3, and over window aggregates. And I think the only thing left is the table API for that. Retract, we also target for release 1.3, basically support all the existing operators. And unbounding streaming group by, it's bundled with Retract. It's dependent on how much work we have done for the Retract. And the last one, streaming inner join, we haven't decided yet. That's all. Thank you.
Any questions? Yes.
Do you support other syntax like a case, a when case, like a kind of conditional manipulative?
Oh, okay. So the question is, do we support other things like a case, when, such other keywords? That's a very good question. But with the introduction of user-defined function, this is actually not necessary, because in user-defined function, you can write your code in Java and Scala. These things are trivial to do.
Well, the difference, like writing Scala code versus SQL code, so you're switching. If you have a case when that's kind of like still SQL, there you're just switching the code.
So this is so in the case of text SQL, there is a transition. Like sometimes you write in text SQL, and sometimes you write your function as Java, right? But this is the thing. This is the good thing about Scala. In Scala, it's actually purely Scala. You always stay in Scala. It's possible that we introduce it, but for now, it doesn't really add new functionality. Maybe something we can look into in the future. Yes?
At a large scale, conversion between payment and performance?
Oh, yeah. So this is a really good question. The question is, at large scale, what's the performance characteristics between the conversion of a string to dynamic table and back? This is one thing I want to emphasize. When I say this conversion, this apply and changelog operation, these operations are not real operations. They are imaginary. You do it in your minds. It's cost-free. You do it in your minds. So when you have a set of strings, you want to describe your computation logic. You convert these into dynamic tables in your minds, and also convert the output string into dynamic table in your minds. Then you do the SQL. Then you imagine how you can write this SQL to express your logic. Then you are done. You never do the actual conversion in production. Yes?
Maybe it's not so important, but why was it you make the distinction so much at the beginning about a static table versus a dynamic table?
Oh, yeah. Yeah, so if you come from, so the question is, why did I make a distinction between static table and dynamic table? If you are from database background, this distinction may seem arbitrary, because in database, every table is really dynamic table. But in big data community, usually, like in Hive, when you say you have a table, people usually consider it as static. When you do batch jobs, when we say batch jobs, it usually means a batch job in a big data scenario. In that case, they always deal with a static table. Yes?
Any consideration of batch string?
So the question is, any consideration of batch and string join? Yes. A batch and string can be joined. Batch string join can be realized in two ways. The first one is you can use a user-defined table-valued function to do such a join. So for you can consider like for each record in the stream, you can do a lookup in the batch side to decide what records you can join to. Another way is you can consider the batch side as a special case of string. It's a table, it's a dynamic table that stops changing after a certain time. So if you feed the batch table initially as a string to the string-string join, the string-string join will give you exactly the same result. Yes?
For the string and string inner join, how large can be saved in the memory?
So the question is for the string-string inner join, how large?
Basically, you're saving two tables. And,
how large can we save it in memory, right? So this is really points to the power of Flink's runtime. In Flink, it supports multiple state backend. The records are stored in the state backend. In Flink, we have memory-based state backend, but we also have RocksDB-based backend. With memory state backend, the amount of records we can save is limited by your memory, but with RocksDB, it's really only limited by your storage, which can be orders of magnitude larger. Yes?
I didn't say any like a Windows kind of a function in your right way to join. Since your stream is continuing coming, it's never end. That cause any problem, no matter how many memory you have, eventually you cannot hold everything in there.
That's a very good question. So, Xiaoxuan, do you want to answer it? Yeah.
Go ahead.
Okay. So the question is, in all our examples, for example, in the string-to-string join, we never have any windows in that. Could that be a problem? Because as time goes by, you may get more and more data. The data may grow indefinitely, right? How do you handle it? That's a very good question. The usual way to deal with such kind of thing is by introducing some kind of window which sets up some bound on the size of the data. This is necessary if your semantics require it. But in some case, it's not really. You really want to do this join over all the time. So in this case, the user really need to make sure the state is finite. The state is finite does not mean the string is finite. For example, in the word count example, the amount of words, distinct words, is your state. This is finite. It's only the dictionary. But the words can keep coming forever. So it's really the user's responsibility. The first answer is it's really the user's responsibility to make sure the state is actually finite. The second thing is it's in the case it's not really finite but close. You can do approximations. For example, you can say my data expires in 1 day. Then that effectively says a cutoff.
Last question.
Okay, last question.
Yeah, sorry about that. So I think it's a follow-up question about this. So if it's a finite state, I can understand that. But for the streaming, so how can we do this capacity planning on this?
Yes. So the question is, if in the use case it's finite state, he can understand it. But in the case of streaming, how do we do capacity planning? That's a very good question. I think the answer is you really need to understand your business. You have to understand how much data your business is needs it. So in the future, we may be able to dynamically scale our jobs. So the capacity, the job will automatically be scaled up when your state grows, but you still need some planning for your capacity because you don't want it to grow indefinitely. If you are worried, you can set some TTL, which will be a practical solution. Okay, thanks everyone for coming.